Nice background, Brittany. That's more exciting than mine.
Our company's having a Zoom chat session this week, and it's supposed to be like our favorite movies. So I've been playing around. I have a couple different ones. So
nice.
We're back. It's from like the 90s. It was like a really short Steven Spielberg animated movie.
Nice.
I watched it at my grandparents' house. So
I was having fun with like some. Is that one? I have this one. This is a little.
That one was good.
Yeah, it's really what I had like some other ones in here too. I think I removed them.
Yeah, I've actually never seen Tiger King. I see all the memes, but I've not watched it.
No, don't do that. It's yeah, I don't know. I felt kind of like gross watching it, honestly. This is so bright. Like it's good to have front lighting to like help with the camera, but then it's like so bright in my face. Yeah, I'm a little darker there. That's all right. Oh, I should close the door so the kids don't bug me. Hold on. Yeah, I turned off the waiting room because like it seemed like the password is enough. So hopefully we won't get bombed anymore. But they seem to have gotten that under control. Oh, let's see here. I should start sharing, I suppose. Why is this page just gray? That's not good. So where do you work, Brittany?
I work for AOE Solutions in St. Charles. So we replace or we house families who lose their home.
Okay.
So I just book clients' hotels the second they have something happen.
Wow.
So yeah, they moved us remote right after the campus closed, or the week that the campus closed, they started to move us out. So we've officially been working from home for the last month.
Wow.
And then we will not go back into the office until the stay-at-home order is fully lifted for all businesses. So my owners basically were like, we probably won't be back for at least the summer, possibly some part into the fall. So just get used to this.
Right. Well, and it's looking like that for us too, honestly. The administration is forming like planning teams for next fall because it was obviously a little haphazard for this semester. So they're like, look, we're not going to wait. And then all of a sudden in July, oh, we need to be online again. Like they're going to plan. So it's looking more and more like there's no official decision, but it's looking more and more like we're going to be online. Thanks, Akshi. Yeah, so we'll see. I feel like the worst is for lab courses because I don't know if any of you are in lab courses. One of my students, somebody else in this class, was emailing me about how hard it's been to try to even do some of those, and some of the classes are not going to be able to finish. I don't know how they're going to. I don't know, like in a class that works on a cadaver, like that's the whole point, like anatomy and physiology. So I don't know. For us, it's like we can survive. We can move a class like this online, especially if we have more planning time. So I think it'll be like, I think fall will be better, but it's not ideal.
Are you going to keep teaching Calc 1 and 2, or Calc 1 and 3?
So it's a good question. I'm not really sure. So I'm slated to teach college algebra, stats, and Calc 2 in the fall. That's my schedule. We pick like way far out in advance. Like we picked that, I don't know, it's months ago. So we usually pick like a year out. But I think what they might do is if the college goes totally online, they might go through the course selections process again and re-select stuff. And the reason why I'm hesitating is like taught Calc 3 this semester, and so I've spent all this time making all these videos. Like I'm making videos for that one. Obviously, I'm not for your class, but so I don't want to do Calc 2 because then I'd have to start from zero, making new stuff for them or finding new stuff for them. Whereas for Calc 3, like I already have half the course, I could just record the rest in the summer, and then my semester would be much smoother because I wouldn't have to spend all this time recording videos. Like it's each video that I make for that class is like 20 minutes, 25 minutes of recording. And then I have to edit out the mistakes and like the kids in the background. Like I had to redo that. And then I'm also doing I'm doing cool effects. I don't know if I showed you these, but I'm doing I'm using my green screen and then showing myself. And so it's kind of extra editing, but it gives me something that's entertaining. It gives me something to do. Am I sharing my screen? No. Yeah, I am. Right?
Yeah, you are.
Yeah,
you are.
Okay. So I could just pick one here. This is all Calc 3 stuff. But there we go. Come on. Look there. So you can see because of the green screen, then I can put myself over the top of the writing.
Nice.
So it's kind of cool, but it takes some editing. And so I'm probably spending 45 minutes on each video, and I don't want to start from scratch. But yet, on the other hand, I would love to do Calc 2 because I know exactly what happened this semester. Like some of my colleagues are like, we have to hold everybody to the same standards because they have to know all these things for next semester. I'm like, or everybody who's teaching next semester could just keep in mind that there's stuff that's not going to be totally learned from spring semester. Come on, be realistic here. Come on. And so if I was I could trust myself more. If I'm doing Calc 2, then I will know. I will only I see on the class list right now. There's already people signing up, and maybe they signed up because they wanted me.
Mm-hmm.
So I feel bad switching. So I haven't really decided yet. And I could do that one. I could record all those videos in the summer too. But anyway, so my schedule is college algebra and stats and Calc 2 for the fall. That's my current schedule.
Professor K, was there a change in the summer courses?
Yes. Yeah. What they decided is, well, at least my dean, I think it's been a little inconsistent across divisions, but my dean decided only classes that have been previously approved to be taught online will be taught online this summer. So this semester, everybody just moved online, but usually there's an approval process where a faculty member has to submit a plan, that plan has to be approved, and there's this whole development process. And so she decided, you know what, we have time for summer. If you want to, if this course needs to be online, we're going to do an approval process. But she didn't really do a call for everybody though. Which classes do you want? They kind of just said, well, these are already approved. And then I don't know how they picked, but they picked 2 more to approve also. So I think it's similar in other divisions. If the class wasn't taught online before, they're not going to do it this summer. And I think so there's definitely a bunch of stuff got canceled.
So Calc 2, last time I was checking, Calc 2 was not approved, right?
No, and I asked hey, we have some students who really need this. I would do it for them and quickly develop a course for summer, and the dean just said, nope, summer schedule is set.
Okay.
So,
all right.
Yeah.
Yeah, I tried doing priority registration and trying to go and hunt down what classes was available and wasn't available was a nightmare.
Yeah. And a lot of that changed after registration had already started.
Yeah.
Yeah.
I just ended up taking Calc 2 at Heartland. So
there's other institutions that have them online already, and it's just kind of, I don't know. The math department here has just been kind of nervous because we see our success rates in online classes, and they're just not great. And so we think that it's just not a good service to students to do some of these higher level courses online. But right now it's different. Obviously, if we have to be online, we'll do it. We'll make the best course we can, and it'll be online, and it'll be okay. So so that we don't have a lot of classes on the books already that are already approved to be online. But we're certainly, like, we should have we'll have a full slate of courses in the fall, one way or another. So,
For the fall, is it going to be online?
there's no decision yet, but all the administrators are planning. So they're partly planning because they're pragmatic and they don't want to have an emergency decision like we did for this semester. But I think they're partly like, you know, so many people in such confined spaces that there's still not going to be a vaccine. And there still probably isn't going to be, you know, 20,000 tests done every day. So, because the problem with the testing is you can test and you don't have it, but then you go shopping and then 2 days later you have it. So you have to have not just tests for individual people, but you have to have the ability to repeatedly test. And we're nowhere close to that yet. So that's why I think they're already leaning toward going online in the fall. So I would actually be surprised if we went to campus in the fall, based on not my knowledge. Yeah, not based on my knowledge of the pandemic. I don't know. I'm just reading the news like everybody else, but based on the discussions that I've heard from my boss and from my boss's boss. Yeah, they're already talking about that. Because
For the fall, that's sad.
It is.
But I'm not going to school anymore.
Are you? Why is that, Sandra?
No, because it's so different to learn everything online.
It's not fun. No. Do you have something to occupy your time with? Do you have some work lined up?
No.
Not yet. That's okay. Yeah, and it's interesting for me. So did I tell you that I got a sabbatical for next spring? I don't know if I told you guys that. So they have, I don't know if you know what a sabbatical is, but you submit a proposal and then sabbatical is like rest, like that's the literal translation for it, but you don't just like have a semester off. You have to do a project. So I'm going to do a project. Oddly enough, my project that I got approved for was videos. Now it was for my stats class, and I was looking to do, I have my stats class is one of my favorite ones to do, and I like to look at a lot of really pressing social issues and incorporate real data from them and use real data for those. I think that makes it more interesting to see how that's really applied. And so I was going to do, like, some of that just takes a lot of time to research, make good videos that are like graphically, not just like writing on a screen or not just clicking through PowerPoints. So it takes a lot of work and research to do all that. So that's why I'm like, I can't do that while I'm regularly working. So I applied and I got approved. So next spring, I'm already going to be off working at home. So it's just going to be a weird year. All right, so back to it here. I guess that was enough casual talk. So my plan for today, I wanted to tell you about the exam. I have downloaded all of your exams. I have made the video key. That is the progress that I have made. That was the downside of having them due by the end of the day on Friday, is that I've had to work. I'm sorry, I'm not grading all weekend. Sorry, I need my weekends. And then yesterday I had class, and so I haven't graded them yet. I'll work on them. I'll have them before Thursday, and then we'll do the reflection like a week from Monday or something, like next Monday, something like that. I wanted to start today by talking about some of the big ideas from 5.1 and 5.2, like a little mini lecture. And then let me make sure, hold on to make sure that I'm recording. Yes, I'm recording. And then we can take some question time and have some extra practice examples if we want those. We'll have a quiz after class on Thursday on these area problems, all these rectangles from 5.1 and 5.2. Let me review the schedule. So Thursday, again, I'd like you to watch 5.3 for Thursday. We'll go over questions, and then we'll have quiz 10 on 5.1 and 5.2 will be posted after class. And we'll keep doing the same thing. I don't know if you've noticed, but the quiz problems should look exactly like the problems that you're doing in the homework, but I'm picking like 24 and you had 23 assigned. So I'm picking an even one that's just like the one you had assigned. We have two more sections. 5.5 is a big one, so we're going to try to do an extra day on that one. We're going to go over 5.5. So next week we'll do 5.4 and 5.5, and then we're going to do that again on Monday. That's a new class that we added because that finals week, you just have Monday, Tuesday, Wednesday. So we're going to add an additional Monday class. And then Tuesday will be review. I'll post the final exam, and then it'll be due by the end of the day on Wednesday. So we're in the final push here, a couple more weeks, limping to the finish, and then we'll be done for the semester.
So was there no exam for chapter 5?
Nope. It'll just be part of the final. So the final will have there'll be at least one question from every section in chapter 5. So 5 or 6 questions from chapter 5 on the final. And then the rest will just be like, a couple from chapter 1, a couple from chapter 2. And so chapter 5 will be totally on the final, and the other ones will be kind of snippets. Okay? Any other schedule related questions? Okay. So let me talk about some of the big ideas here from 5.1 and 5.2. The first idea, and we can do some examples later, and maybe you'll ask some homework questions. One of the main questions that we are looking at here is if I have a function, and I'm drawing a function that has positive y values here. It doesn't have to be positive, but to introduce the idea, it makes more sense if it's positive. How can I find the area under the curve between two particular x values? That's like the big question we're trying to answer here. Now, it has a lot of different applications, just like the tangent line. Remember the tangent line? It's like, oh, it's this, the derivative is the slope of the tangent line. But then the derivative became like this 2.5-month investigation that we've been working on ever since that had all these other applications. So the area problem is the same thing. Like, that's how we're introducing it. There's this area underneath the curve question. But there are much broader implications. So the way that we first talk about this is, I can kind of erase my shading, is we say, you know what if we broke it up into, like, say 4 intervals, break it up into 4 intervals, and then we'll draw some rectangles. And there's different rectangles you could do. You could do rectangles that are all underestimates. So I'm going to go, I guess all the underestimates would be left endpoints this time. And then you could find the area of those 4 rectangles, which is just the width times the height. And the height is just the function value there. So whatever, like that first one, that first area would be the width, whatever the width is, some change in x. We'll call it delta x. So delta x is the width of each one. And then the height would just be, for that first one, it would be f of a. So you just width times height for each of them, and you add them all up. That one, of course, if we added those 4 rectangles up, that would be too low. It would be a lower estimate for the area. We could also do right-hand endpoints here, upper ones. So if I draw a red one here, you could go to the right side for each interval. And you can see that those are too much. Those are extra, those red ones there. But those, we would call those an upper sum. So there's some notation in the book that's not super important, but just to explain what the book means. The lower s sub n, lowercase s sub n, is a lower sum. That's the blue ones. And then the red ones here are the upper sum, a capital S sub n. And the key here is the upper sum is greater than the area under the curve. And the lower sum is less than the area under the curve. And so a classic question that you'll be asked, and if you've looked at this homework, you've seen it, is they'll just ask you, find a few rectangles and add up their area to estimate the area under the curve. So that's the big idea. Now the question is, how do I get more accurate? Like, what if I want the actual area under the curve? So I don't know, did anybody get that from the videos? Like, what if I wanted to improve my accuracy? How could I improve my accuracy?
You multiply the number of rectangles you have.
Right? So you could, like, what if I get more rectangles? So I have this link, I posted it on the homepage right now. It's called this Visualizing a Riemann Sum. Visualizing a Riemann Sum. If you want to open it up and play along, you can. You can just watch me do it, that's fine. It's this applet. So I've got that page open right here. And I have this really funky function here. Let's make it positive. This one happens to have some negative terms here. All right. Oh, I got really positive. Can I zoom out? I don't think I can zoom out. Let's divide by, I'm trying to change the function here just to make it a little more visible. There we go. So here I have these rectangles. And what I'm doing here, let's see, so these are doing right endpoints. Right endpoints, you'll see each one, the height is using the right endpoint for that interval. And so what Christopher is saying is, well, there's all these errors here. This is not going to be the area under the curve. If I do lower sums and upper sums, the lower is not always the right endpoint or left endpoint. It's just always underneath, whatever that would be. But that's definitely wrong. The upper sum, definitely too high. They're all over. And here's a relative one. I could use right endpoints, left endpoints, midpoints. So none of those are correct. But here's what's interesting, is if I have more and more intervals, so you'd need a technology for this. Can you imagine trying to find the area of 60 rectangles? No, not good, not good. Look at that. When I go up to like 100 rectangles, it's really, really close. It's really close. And that's using left endpoints. If we do right endpoints, or midpoints, or upper sum, lower sum, some random point in the middle for each one, pick a random point in the middle. It doesn't really matter what you do then. They're all really, really, really close. Okay, theoretically, what if I wanted the exact area? This is better, but what if I want the exact area?
You would use the limit as n approaches infinity.
What is n though?
The number of rectangles.
Right, the n, the number of subintervals here, n, if I have infinitely many that are infinitely small, that gets me that. So there are a couple of videos that I marked as optional that talk about and actually show you how to do that for a couple of specific kind of simple functions. It's worth investigating if you're interested. It's kind of like the definition of the derivative, where actually, because we do that a little more often. It's more like the limit definition. I don't even think we ever used it. We talked about it very briefly on one day. Do you remember the epsilon and delta? And like, I don't know if that sounds familiar. Like, it was kind of just the idea of it. And that's kind of what those are. But it's worth investigating. But I'm not going to have you actually do that limiting process. You will not. I changed some homework questions and asked you to remove a couple here. You can skip these. So you're not going to actually have to take the limit as n goes to infinity, but it's important to really understand what that is. So let me go back to the notes here. So if we wanted the actual area, well, here, let's do it. So the approximate area would be a sum, and there's this Greek letter sigma, a sum of f, the function value at some point in the ith interval. Now I was using, you can use left endpoints, right endpoints, any point in the middle, times delta x sub I, the width of the ith interval. That's the approximate area. You just add up all these rectangles, and the rectangles would be, the height would be a function value at the x, and then the width is a delta x sub I. And then the actual area, there's two ways to look at this. I'm going to write this way. Sum I goes from 1 to n of f of x sub I, delta x sub I. And then I like what Christopher is saying about the limit as n goes to infinity. The downside of that is that only works, and this is what was true on the picture, that only works if the delta x are constant. Like they're all, if you just take the width of each one, if you just take the whole interval, b minus a, and divide by however many there are, because then they'll get infinitely small. There's some little more abstract theory here that says, well, they don't have to all be the same. So the official definition is I could take the limit as the maximum width. I need more space. Hold on, I'm going to cheat. You take the limit as the maximum width goes to 0. I want to show this just so you kind of have a very vague idea of this. If you're a little lost here, it's not going to affect really the quality of what you can do moving forward, but it might help a little bit to understand what's happening. So this will give us the actual area under the curve. We add up n rectangles, and you have the height f at x sub I, where x sub I is some point in the interval, then the width delta x sub I, and the delta x sub I can all be different. So you could have a really wide one, delta x sub 1, and then you could have a skinny one, delta x sub 2, another wide one, delta x sub 3, etc. They don't all have to be the same, but to get the actual area, the biggest one has to go to 0. The largest interval has to go to 0 eventually.
I have a question.
Mm-hmm.
Why would you want to make the lengths different sizes? Wouldn't it just be easier to have them all the same size?
Totally easier to make them all the same size. And you almost always do. But in theory, they don't have to be. So this is like a very abstract way to look at it. When you make them all the same size, it makes your life easier. But the theoretical point only here is that you don't have to. You can still get the area if they don't all have to be the same size. But your life is definitely, it's way easier if they are all the same size. You're correct.
Is there any time and point where you would have to use this?
No. So this is just basically a very abstract result. In fact, I'm trying to think. We do this idea of breaking the interval up often, and we do this a lot in Calc 2. Calc 2 does a lot of this, but they don't actually find these limits. They have other strategies that you're going to learn coming up here this week and next week about how to actually compute these. You don't actually take limits of sums. It's like the definition of the derivative. You don't actually take the definition of the derivative for every function. You have all these derivative rules. And so I think every example I've always done, you are always able to do equally spaced intervals. Yeah, you're always able to do that. So there's no time that you have to make them differently with different widths. No. So the connection then that we're going to talk about now is that area, that actual area, can also be defined as something called a definite integral. And the definite integral, I'm going to write the limit thing here. Max delta x sub I goes to 0. The sum I goes from 1 to n. F of x sub I delta x sub I can be just defined. It's just a definition. That's all it is, just a definition with this elongated s. So like, think like the sum. So you have this Greek letter sigma that stands for a sum. And so here I have an s that's kind of stretched out, and it's the sum from a to b of f of x and then the differential dx. And those two things are equivalent. The one on the left is I guess they're all abstract, but the one on the left is like the idea behind it. And the one on the right is just more a notation like, well, we're going to call that the definite integral, and that's what it's called. So when you see this thing on the right, it's not bad to just think of that as the area under f of x between a and b. Now I have a caveat. You have to be a little careful if the function has some negative values. Then it's not really good to interpret it as area, because area can't be negative, but a definite integral can. If you look at the definition here in this sum, it just takes the function value times the width. So if we made a rectangle here on this one, the function value would be negative, and that is a-okay. You can get a negative answer there. So definite integrals can be negative. So the area, I'm going to put a little asterisk there by the area. Little asterisk there. That's if f of x is always greater than or equal to 0. So it doesn't represent area if it's negative, because you can get a negative answer for an integral. So it's a little bit, you got to be a little bit careful with that. But that's okay to, when you're first introducing it, to think of it like that. So 5.1 and 5.2, the main goals we're going to have here, and hopefully we'll do some examples here, is can you estimate the area under a curve with some rectangles? Usually like 4 is a good quiz thing, because it's a little tedious. If you can do 4, you can do 8. It's just more work. So estimate the area under the curve, and then connect this definite integral thing to area. What's that connection between the definite integral and area? And like I said, I have some examples about that as well. So I thought this is such a big idea, it'd be worth us doing like a little brief mini lecture. I know Dr. Scherger talked about these things as well, but they are very abstract, so I thought that would be worth us investigating. I want to do some homework questions next, or some examples, whatever you prefer. But before I do that, does anyone have any clarification questions that you wanted to ask about what I just was talking about today? All right, I am not seeing any. Okay, so let's talk about homework questions then. I think that probably is best. I do have some examples that might be better, I don't know, but let me pull up the homework here. 5.1. Okay, so let's start with 5.1. You can type in the chat, or just raise your hand, or just unmute yourself. Oh, Haley's fast. 19. Okay, this isn't one of the ones I took out. I don't think those are in the 20s. Yeah. Okay. Okay, so Haley, if it's okay, you see how this one asks you to do 4 and then also 8? I'm going to do the 4 with you and then leave the 8 for you to do on your own. Whoa, really big. All right. So we're going to approximate the area under the graph of each function from a to b for n equal 4 and n equal 8 by using the lower sums, all the rectangles that lie below the graph, and then the upper sums. All right, so really important here is to draw the graph. So let's draw the graph. 16 minus x squared. 16 minus x squared is a parabola opening downward. Has a y-intercept up here at 16, and then it's a parabola opening downward. I don't know why. I'm going to stretch it out a little bit. And it goes down like that. I don't really need to draw the left, because I'm only looking from 0 to 4. And coincidentally, well, no, I'm sure they did it on purpose. Not coincidentally, this one's x-intercept is at 4. Right, 4 squared is 16, so 16 minus 16 will be 0. Okay, so let's look at letter A. We're going to use 4 rectangles, and we want to find the lower sum. So we could use notation here, S sub 4. I'm going to draw those, and I think we'll need drawings each time. Like if I were doing this for the homework, I would have 4 drawings by the time I'm done. 1 for lower, 1 for upper with n equal 4, 1 for lower, 1 for upper for n equal 8. So 4 total drawings. Okay, lower sum means for this first interval from 0 to 1, I need to make sure my rectangle is below the curve. So where should I put the height? Should the height be at 0, or should the height be at 1, or somewhere in the middle?
Zero.
At 0, if you draw, can you see you're going to be above the curve? I don't know if you can see that there. It's a little hard. Let me zoom in. Right, because at 16, at x it's 16. So the lower sum doesn't mean the lower endpoint of the x value. What it means is you want your rectangle to be below the curve. So we actually need to use 1 for that one. And it feels weird, at least it feels weird to me, that the lower sum is with the upper x value, the higher x value. But it's all about making sure that your rectangles are below the curve. Your area has to be an underestimate here. Does that make sense, Christopher, why that would be?
Yes, I was just going to ask you because mine actually has that, but I forgot that I didn't use 0. I used 1.
So you knew it, you had it right. Just kind of, yep. It's all good. Okay, and then the next one, it looks like we'll just follow this trend. So at 2, we would use 2 because we want to be under. And at 3, oh, the last one's weird. What's the height of the last one?
0.
It's just 0, right? Because at 4, it's just 0. So we really only, this is nice, we really only have to find the area for 3 rectangles. I'm going to zoom out here, give myself a little more space. Okay, so this is, we want the sum of the areas. That's what we're going to get. So let's see, height. The height for the first one will be f at 1. And you can calculate that if you want. I'm just writing it out. It would be f at 1. And then the width is 1. And then the second one would be f at 2. And the width is 1. And then f at 3. And the width is 1. Technically, it's f at 4 times the width is 1. But that one we know is 0. This is why the drawing is helpful. The drawing is really helpful for that. Okay, f at 1, we have our function 16 minus x squared. So plug in 1. 16 minus 1 is 15 times 1. F at 2, 2 squared is 4. 16 minus 4 is 12 times 1. And then f at 3, 3 squared is 9. 16 minus 9 is 7 times 1. So we would get, what is that, 22, 30, 34?
I have a question.
Yes.
Why do we start by f of 1 for the lower sum?
Right, I know. This is where it's like the lower sum feels like you should do left endpoints, right? Look at the look in letter A. By using lower sums, rectangles that lie below the graph. So that
Okay.
lower sum, let me go back to the function that we were looking at here, this weird function on this example. Let's go back. We'll just do smallest number of subintervals here. Let's do 4 here. There's 6. Okay. So if I do lower sum, you'll see some of them are the right endpoint. Ooh, this one's kind of right in the middle. This one's a left endpoint. This one's a right endpoint. This one's kind of in the middle. This one's left endpoint. They just have to make sure that they're all below the graph.
Okay.
That's what they're calling the lower sum.
Also, we also have to check, other instruction about it, not only lower sum, stuff like that.
Well, the question is, what does lower sum mean? And so, yeah, so this particular textbook, and this is pretty consistent, but they're defining the lower sum. This is what the lower sum means. So they're assuming for like a later example, they could just tell you the lower sum and not give you these instructions, and you should know that's what the lower sum means.
Oh, really?
Yeah, yeah, yeah. So if you
Oh,
look, yeah, if you look in the textbook for that, they'll define what the lower sum is, and it is always below the graph. So that's different from left endpoints. Using left endpoints, then I would use the 0, the 1, the 2, the 3.
okay.
Yeah, that's a good question. All right, Haley, this was your question. How are we doing so far?
I'm fine with solving it like that. I just tried solving it differently using is it the summation, the E? Should I not do that?
No, don't
Okay.
do that. Don't do that. These you want to just grind out. These are easier to just find the sum by doing it and just find the different heights and just grind out the areas and just do them by hand like that. Yeah.
Okay, thank you.
Yeah, it's not fun using the summation and the ends, and no, don't do that. It will work, but it's not fun. All right. So then you don't need me to do any more? You're good?
No, yeah, I'm good.
Okay. All right, Christopher.
In her videos, Dr. Sugar would use the 34 UN squared. Could you explain to me what the UN stood for?
They're just units because it's an area. So it's some, we don't know what it is, but it's some units squared. So whatever the units are, we don't know what they are, but there are some units squared, whatever the units are. Now, that's not always clear because here it's unit squared because it's area. Later, we're going to say, well, what if this represents velocity in meters per second? And in fact, I think there's some homework questions like this. What if that represents velocity and then x represents seconds? Well, there, if you take velocity, meters per second, and you multiply by seconds, what would you get?
Meters.
Meters. Yeah, you actually get the distance traveled. Isn't that crazy? So if you have a function, if, we'll call it f of t, represents velocity, then that definite integral doesn't represent area now. How do you have area under velocity? It doesn't make any sense. It can't be area. In that case, then it represents the distance that you've traveled, your total displacement. Represents net displacement. Now, I'm just tossing that out here, and that may not make sense to you. That's okay. I'm just just a point of reference. I understand why Dr. Sugar is doing that. If we're looking at area under a curve and f of x and x have the same units, then area would represent some square units. I'm not too worried about the units right now because we don't have any units, and it really depends on what these functions represent. So that will be more important in some later examples. And I feel like there are some. I think it's in 5.2. It's in 5.2 where there are some units. Yeah, it's not 5.1. There are no units in 5.1, but in 5.2 there are some units. I remember looking at those. Does that answer your question, Christopher, about the units?
Yes.
Okay. All right, and then you had a question about number 13.
Yes.
Okay, let's do that one next. Number 13. Okay, let's see here. I'm gonna box that one. Oops, nope, I gotta do. Let's see here. So hard, my office door is glass. And so out of the corner of my eye, I can see an 8-year-old child looking through the window. No. This is the universal symbol for can I play Xbox? Oh, buddy. And it's like beautiful out. I'm like, dude, so nice out. Go outside. So my guess here on this one is it's going to be similar, but we're not given a function, and we're only going to need to, we're only going to have the graph to do it here. Lower sum, again, notice the lower sum rectangles below the graph, upper sum rectangles above the graph. And I think they're giving us, it looks like they're giving us, we have to use 4 intervals here because that's the information they're given, because those are the function values. So we're actually going to do S sub 4, and then we'll do capital S sub 4. You can't really tell my lowercase s until I do the uppercase S with the little tails. So let's do the lower here. I'm going to draw on here. I'm going to have to use a left endpoint for this first one. That'll get me under it. The next one would be a right endpoint. That'll get me under it. I'm actually going to use the exact same point for the third one, and that'll get me under it. Oh, and then the last one is 0 again. That's the only way to get under it, is to have 0.
You answered my question. I just wanted to know how to do this. Now, this goes back to the video Dr. Sherg was saying that when the function is increasing, it's going to be, and you want the lower sum, it's going to be the left. And when it's decreasing, it's going to be the right.
Yep,
Okay.
and the only challenge is if in your interval it's both, then what you would do is you would pick the whatever that relative minimum is.
Okay.
You know what I mean? Yeah. So it's, if the function's always increasing, it's easier, and always decreasing, it's easier. It's a little bit harder if it goes up and down. Then you gotta be a little more careful. And yeah. Brittany, were you gonna ask something?
For the uppers, then we would use the higher points. So we would use like 5 to 2, and then to make that. Okay.
Yep. We'd use 5, and then same on the other side, and then 7, and actually 7 on both sides there too.
So the 0 doesn't apply when we're doing the upper. It only applies for the lower. Okay.
Yep.
Would use, it would be 2 times f of 0 plus f of 4 plus f of 4 plus f of 0, plus f of 8.
Yes. For your lower one, right? Yep. Yeah, so, and you could even say, Christopher's kind of getting a head start. Let me show what he did here. So 2 times f of 0, which was 1, 2 times f of, I'm doing the blues here. 2 times f of 4, which was 3, another 2 times f of 4, which is 3, and then a 2 times f of 8, which was 0. And he is noticing, like, well, all the width is always 2 on these, so why don't I just factor out the 2, and you just get f of 0, f of 4, f of 4, f of 8. So they all have the same width, you can just factor it out. So, yeah, that's a good recognition there. We did not do the upper, but it's the same idea there. Any additional questions on 13? Okay. Any additional, we're still working on 5.1. Any additional 5.1 questions?
$21.
All right, let's look at 21. Let's see here, 21. Oh, this is similar to 19. Oh, notice the graph here. I think there's a hint that we're going to need some technology for this one. And we have to do n equal 4 and n equal 8. I think the 4 we don't need technology for, but the 8 we will. Any particular part of this you want me to focus on, Christopher?
The graphing and the sectioning off of the lower sums.
Okay, that sounds good. So let's see, cosine of x just from negative pi over 2 to pi over 2. And feel free to use technology here, but I think you all should be able to know that it's just kind of like a little, almost looks like a semicircle there. It's not, of course, it's part of a cosine curve. But that's the cosine starts at 1 and then goes down to 0 at pi over 2, -1 at pi, and then on after that. All right. Does the 4 or 8 matter for you, Christopher? Is 4 fine or?
Yes, I went with the 4.
Okay. So we'll do lower sums. Okay, so we're going to split into 4 intervals. So that means we have -pi/4, 0, pi/4, and pi/2. And we're going to use lower sum. We want all of our rectangles to be below the curve. So we're going to have nothing for the left one. And then whatever it is at -pi/4. And then we need to be below. So now it's going to have to be at pi/4. And then nothing for the last one. That's the lower. So if we were to write them all out, it would be, let's do the width of 2. They're not a width of 2. They're a width of pi/4. So pi/4 times cosine of negative, no, sorry, cosine, yeah, I guess you could say cosine of -pi/2. All right, that's going to be 0, plus pi/4 times cosine of -pi/4, plus pi/4 times cosine of pi/4. So if we label these 1, 2, 3 is 1, 2, 3, and then 4 is the last one. And again, it's going to be 0, but I thought it might be worth labeling it here, cosine of pi/2. That's the 4th one. So it's really, there's really only 2 rectangles that have any area there, but just for kind of completeness sake, so we can see it all there. Any questions on the setup for that one?
No.
Okay. And if we finish it with pi/4 is times 0 for the first one. Pi/4 cosine of -pi/4 is square root of 2/2. And then plus pi/4, another square root of 2/2. And then pi/4 times 0 for the last one. So it looks like we get, well, it's pi times square root of 2/8, but there are 2 of them. So it's really pi times square root of 2/4. Yeah, what a weird number that is.
I did the change in x, and for my change in x, I had a 2pi/8, and then I multiplied that by f of -pi/2 plus f of -pi/4 plus x of pi/4, then plus f of pi/2.
Mm-hmm. That's the same. Yeah, it should get, that's.
Could you show me how to do this that way? Because I was given the negative, it was negative square root of 2/2 plus square root of 2/2. And that would have given me 0.
Yeah, but this isn't, cosine of -pi/4 is not negative. It's positive. It's positive square root of 2/2. You can even see it on the graph, right? They're all positive. It's definitely positive. Those
Okay.
y values.
Yep. All right.
If you think about the unit circle, you're down here, but you're the x coordinate. And so the x is still positive there at -pi/4.
Thank you.
Yeah, no problem. No problem. It's so weird to see the negatives and then you forget, wait, that's the x value, but my function value could still be positive there. All right. Any additional questions here on 21? Okay, any other questions? Maybe let's talk a little bit about 5.2. We have Thursday to answer questions from 5.1 as well. But let's move on to 5.2 so we can talk a little bit about that. I have examples if there are no questions. But did anyone have any questions you wanted to bring up from 5.2?
I have a question dealing with the examples. I haven't gotten to the homework yet.
Sure, no problem. Which like from the book examples?
Yes.
Mm-hmm.
It was the example 1, finding the remain sum.
Riemann sum it's called. Yeah, Riemann. Yeah, German. Nice German name.
I understand the first part, but I was confused by the taking the midpoint of each sub-interval.
Yeah, what that's saying is, if we go back to our little graphic here, let's use the function they have. X key, what? That was weird. It just like jumped. Okay, that's annoying. Where'd it go? That was so weird. I was like looking at it and then it jumped. Oh, there's our man right there. Okay. The function is x squared minus 3 from 0 to 6. So I'm going to go here, x squared minus 3. And then we're going to go from 0 to 6. And we need to zoom out a little bit. Okay, so we talked about lower sums. And I think, did they do that, or did they do left endpoints, or what did they do first? Left endpoint and then midpoints. So left endpoints would be relative here, left endpoints. And so there you just go for each interval. Let's see, if we're going to 6, and we have how many subintervals do they want us to do? 4 subintervals. 4 subintervals. Oh, but they're doing different widths. Okay, so it's not quite what I'm going to show here, because they're doing different widths. So I apologize for that. It's not quite the same. So I did 6 intervals here. And so left endpoints would be at the left endpoint. That would be your function value. That would be, you'd multiply the width as 1 by the left endpoint. So when you talk about midpoints, all you're doing is you're finding in each interval. You can see here, do you see, I don't know if you can see, it's really still kind of small. Do you see the 2.5 here? And then you go up to the function and they're drawing the rectangle at the function value at 2.5. So they're using the midpoint of each interval to get the height for that interval. So
I have the midpoint between those intervals. I was confused by, they were multiplying it by the change in x. Because in the original in A, they were just plugging that back in and then getting it and multiplying it.
That's what they're doing. That's what I see here too. So are you looking here in letter B?
Where did they get 1, 1,
2, and 2? That's the width of each interval. So they're finding the function value at the midpoint. That's this negative 11/4, and they're multiplying by the width of that interval. They still need to get a rectangle. So you still need to find the area of that rectangle. And so, but they're not all equal width. So the first one is width 1, the second one is width 1, the third one is width 2, and the last one is width 2. And then the heights of the rectangles are the function values at the midpoints.
All right.
So they have your function values, and I think it sounds like you got those okay. It's the function values, and that's these negative 11/4, the negative 3/4, the 6, and the 22. And then that's the height of the rectangle, and then the widths are the 1, 1, 2, and 2.
Are these the widths between the midpoints, or are they still the widths of the first ones?
Still the width of the interval. Not the widths between the midpoints, but the widths of each interval. You're still, here, let me jump back over here, just in general. So let's say I have a function here. I'm going to go from A to B. I'm going to do 4 intervals, okay? So let's make some numbers here. We'll call it from 1 to 5. So delta x, the width of each interval, is 1 because there are 4 intervals and it goes from 1 to 5. So the delta x is still always 1. And then what I would do is I would say, well, let me find the midpoint here, which is 1.5. And I'm going to call the height of that rectangle. The area then would be f at 1.5 times 1. It's still a rectangle, and it's the width of that interval, not the width between the midpoints.
Okay, so the width stays the same. All right.
It does. Yep, the width stays the same. All right. Sandra has a question from number 19 from this section. Let's go down here. Scrolling, scrolling, scrolling. Okay, so this one is a notation question. And it's all about figuring out what in the heck are you giving me? What does this actually mean? Almost shrunk it down enough. All right. So let me go back up to the beginning of the day when we did this. Ooh, I can cheat again. Look at this. Copy. And then I can go down here. I need to add a little more space. Paste. Ah, sweet. Technology can be cool when it works. So this goes back to the notation we talked about. What in the world is this Riemann sum and its connection to the definite integral? You can see here what we have kind of looks like what I've written on the left-hand side. There's a couple of differences there, and it's just a notational thing. You'll notice it's the interval from 0 to 2. So if I wanted to draw what's happening, I would draw it from 0 to 2. And you can see there's still the max as the delta x sub I goes to 0. It's a sum of n rectangles. And so the question we have here is, what's the function? Because I can see it goes from 0 to 2. So I know the integral is going to be from 0 to 2, because those are the x values. But what I don't know is what function am I finding the area under? That's really the question. And you can see here, do you see the e to the u sub I plus 2? It's not quite what I've written here, f of x sub I, and maybe I should have been a little more careful there. The textbook, they're using u sub I to represent some x value. This is why I use x sub I, but they're using it to represent some x value in the ith interval. So the key is that it's an x value. So this e to the u sub I plus 2 is really saying that the function is e to the x plus 2. So that thing on the left is the area under the function e to the x plus 2 from x equals 0 to x equal 2. And so the definite integral, the answer to the question is the integral from 0 to 2 of e to the x plus 2.
And for this one, you didn't have to do anything from left endpoint, right endpoint, nothing?
Nope. All it is, you see the directions, it simply says, again, there's a lot of vocabulary here. So like, I'm not saying like, oh, it's obvious, but no, it just says, if you read carefully, write the limit of the Riemann sum as a definite integral. So boom, I wrote it as a definite integral. It doesn't say compute the limit of the Riemann sum or find the definite integral. It just write it as an integral, that's all.
Okay.
Good, good. Any other 5.2 questions? Okay, I'm not seeing any. We have a few minutes left. So why don't we open up the examples here? Do you have a preference? Would you like to see more 5.1, like rectangles and areas under rectangles? Or 5.2, where you're looking at this definite integral idea? What is the definite integral? I thought I had one. 5.1. Sandra was the quickest to act. Is that okay? Is that okay? So let's start here. I posted these, but just a few minutes before class, so you might not have gotten it, but I did post on the homepage. The most recent news post has some 5.1 and 5.2 examples. They're pretty easy to write down if you want to just write it down. So let's see if we can do this first example. That's about all we'll have time for today. Okay, so we're going to use 4 rectangles to estimate the area of the region bounded by this function and the x-axis between x equals 0 and x equals 2 using lower sum and then upper sum. So we're going to draw graphs. We're going to draw 2 graphs. And let's see here, x equals 0 to 2, and it's e to the x, which grows exponentially. It's called an exponential function for a reason. Y equal e to the x. And let's see, we wanted to use 4 rectangles. So I'm going to split this up to, we got 1/2 and then 3/2. And I'm just going to draw vertical lines here for now. Excuse me. Okay, so for letter A, we want to use lower sum. So this is kind of what Christopher was talking about earlier, I believe it was Christopher. If the function is always increasing, which it is here, then we would just use left endpoints. And you can see if we want to get below, I'm going to have to use, that's a terrible line. Oh, and then I lost my exponential function. We have to use left endpoints to get below. It isn't always all the same endpoints, but in this particular case, the lower limits, to get lower sums, I'd have to use left endpoints. So the lower sum will be the width is 1/2, and then why don't you? How about this? How about someone who hasn't answered yet today? You know my trick, right? Can you tell me what the height of that first rectangle will be? So I know Lorenzo, JT, Albert, Sydney have been pretty quiet today. Sakshi, do you know what the height of that first rectangle would be?
Would it be e to the x? Or
It's
e
from,
to the 1/2, I mean?
You're close. You're super close. You're super close. It's from the function, so you nailed it. It's definitely from the function. But we want to use the left endpoint, so we actually need to use 0. So it'd be e to the 0 for that first rectangle.
Oh, okay.
Okay? But yep, you were right. You're going to use the function, so it'd be e to the 0. And of course, everybody knows e to the 0 is 1. So there's the first one. The next one, the width is also 1/2. Let me label these here. 1, 2, and then we're going to have the 1/2 times e to something here. We got to fill these in. That's the third one. So we have 1. That's, you can't even see that. 1, 2, 3, 4. So we have one more. 1/2 e to something there. 4. So how about somebody else? What about the second rectangle? it's going to be e to what value for that second rectangle?
1/2.
That's right, e to the 1/2. Good. What about the third? Any ideas about the third?
1.
E to the first, yep. And then we can follow the pattern here. Hopefully you can see it. Now the last one would be e to the 3/2. And so we need to get a decimal approximation of that. Scientific decimals calculator. What do we have? 1/2 times, it was 1, so we'll just do plus. I guess we could factor out the 1/2, that's fine. But anyway, 1/2 times e to the 1/2 plus 1/2 times e to the first plus 1/2 times e to the 3/2. So we get about 4.92, approximately 4.92. And this is where Dr. Scherger would say, well, there's some, it's area, so it's some square units. If you just put 4.92, it's fine. That's the lower sum. Any questions on the lower sum?
I have a question.
Yeah, go ahead, Lorenzo.
So how did we know to go all the way up? How did we know to use the 1/2 and then 2 all the way up to 2?
Good question. I've been kind of skipping over that. If you just look at the x-axis, the key here is it tells you that it wants to go between, it has to give you a lower and upper limit, because how do you know where to find the area? So it has to give you a lower and upper limit. And here it says between x equals 0 and x equals 2. So then the question is, how do I break it up? And this goes to Christopher's point earlier about, like, why don't we always make them equally spaced? Do we ever have one that's bigger than another? And it is always easiest to make them equally spaced. I think I might even tell you. No, it doesn't. Some of the book examples, I think they might tell you like 4 rectangles of equal width. So I just kind of eyeball it and say, well, 0 to 2 would be a total width of 2. And if I want 4 intervals, then I would just divide by 4 to give me the width of each one. And so that's 1/2. And that's how I knew to go up by 1/2 each time. There's a formula you can write down if you like. You can use the width is, you can call it delta x, and it's just the full width of the interval, b minus a, the full width of the interval, and then divide by how many rectangles you want. And that'll give you the width.
Okay. Thank
Cool. Yep, no problem. So that's how we broke it down. Yeah, we hadn't talked about that yet, and I was just kind of skipping over it. Any other questions on the lower sum? All right, class is officially over, so feel free to take off. I'm going to finish this up, and then I'm going to hang out for a little bit if you have any additional questions you wanted to ask. We'll do the other examples here, and we'll do some homework questions on Thursday, and then you should watch 5.3. I'll put a news post up. I'm going to put that here, a reminder to myself. News post for what to do for Thursday. And then keep your eyes out. I'm going to be working today and tomorrow on grading, so I should have those exam grades up. But I'm just going to finish up here, do the upper sums, and then I'll stick around if anyone has any questions. It's getting nice out. It's like getting warm in my room. I'm going to have to like...
When's our quiz for this?
Oh, it'll be posted after class on Thursday.
Okay.
It'll be these 2 sections, 5.1 and 5.2. And so you can still ask homework questions on Thursday from these 2 sections.
Okay.
Yep. All right. So we're going to do the same function. And we're still going from 0 to 2, and there's still 4. So 1/2, 3/2, except now we're doing the upper sum. And the width is still going to be 1/2 for all of them. I don't know if you recall, Christopher was factoring out the 1/2, which is a great idea. You're welcome to do that because they're all going to be the same width. So you're welcome to factor out the 1/2 if you want to. But now we want the upper sum. And so you can see for each interval now I'm going to use the right-hand limit. So that would be e to the 1/2 now for the first one. And then e to the 1 for the second one. You can label them 1, 2, 3, 4. 1, 2, 3, 4. The third one would be e to the 3/2, and then the fourth one would be e to the second. And again, we can type that all in the calculator, and that's fine. Not really worried about that. Any questions on that upper sum? Okay, well, that is it. That is all I had. I don't want to do too much more, because for those who weren't here, you know, it's a lot to watch. So I'm going to stop the recording now, but I'm not going to end the meeting. I'm just going to stop the recording.